Force, work, and energy review 7. A spring launches a mass from rest. Determine the mass's speed at the top of the hill. This mass comes down here and then goes up, and we want to know its speed right there. We're told that there is no friction. We know the height here is 2 meters. We know it's 5 meters there. Since there's no friction, I'm going to make this the reference line right there for determining gravitational potential energy, which means my system won't have any gravitational potential energy at first. Since there's no friction, we can use conservation of energy. E initial equals E final. The initial energy is all in the form of this elastic potential energy of the spring, which is 1/2 kx squared. There's no kinetic energy, and because I've defined the reference line there, there's no potential energy. At the end, we have some gravitational potential energy equal to m times g times the height that it's raised up above, which is 3 meters. That's the potential energy, but it also has kinetic energy at the top, doesn't it? 1/2 times its mass times its speed squared. So what this turns out to be is, if we multiply this out, we got a lot of 2's canceling. That looks to me to be 480, and that's going to be 300, and that's going to be 5v squared. So subtract that off, divide that by 5, and that's going to be 180 divided by 5, which is 36. Ooh, that's really nice, isn't it? V final is going to be 6 meters per second. Sometimes the numbers come out really nice like that. Now we've got something similar happening, except now we have friction. And we're told what the mass's speed at the top is. And we want to know the work that's done by friction. In this sliding process, we can't be conserving energy anymore because now we have friction. So I think what we want to do is we want to use the work energy theorem, where the work done is equal to the change in kinetic energy. But to do that, we need V initial. So let's find V initial. I'll call it V naught when mass is launched, just as it's launched from the spring here. So we are going to conserve energy right there. Right there, we need V naught. So let's find that. We're going to conserve energy. Initially, all elastic potential energy, 1/2 k, the amount of stretch or squish in the spring squared. All of that is going to be converted into kinetic in those first couple of instants. 1/2 m v squared. 1/2 cancels. That's going to be 960 divided by 10, so the square root of 96. And when I calculated that, I got 9.8 meters per second. All right, now that's not a final answer. That's just the speed that this mass has when it starts to go down the ramp here and then back up the hill. So at this point, now we're going to use the work energy theorem. We're going to say the net work done is equal to the change in kinetic energy. Well, what's the change in kinetic energy? It's 1/2 m v final squared. Well, v final we're told is 4 up at the top of the hill, minus v initial squared, which we just found, 9.8 squared. If we crunch these numbers, we get negative 400 joules. That's the net work done. Now, how is the net work broken down? We're running out of space here, but we're going to do our best. Who does work on this mass? Well, gravity does some work because there's a change in height, and then friction does some work. How much work does gravity do? Can we figure that out? What's the work done by gravity? It's equal to m times g times h. That is the change in elevation, which will be 3. Now, is that positive or negative? Whenever we raise something up, we're moving it up, but gravity acts down, so that's a negative work. Put a negative sign there. Okay, I think we can do this in our head. This comes out to be negative 300. The total amount of net work done is negative 400. Therefore, friction must have done negative 100 joules worth of work. And the fact that that came out negative shouldn't surprise us, because friction always does negative work.